all we need to do is find a pair of frequencies here which differ by 2 hertz, correct? And the only ones that satisfy that are 441 and 443. So the correct answer is C. And yes, 84% of you got that correct answer. Okay, for what we're going to be doing in the coming lecture, I wanted to get kind of a little bit of a head start on it. We're getting a little bit ahead of the DLs, but that's okay because I'm going to go back over this at the beginning of the lecture next week. But what happens if we have waves in 2 and 3 dimensions? Now, we had this nice graphical demonstration of a wave radiating out from a disturbance at x equals 0 and y equals 0 that we talked about last week. But what if we have a second one? You get a little bit of a jitter in the animation here. But I think if you look at it carefully, let it sort of wash over you, you will start to see that there are some different looking patterns here. For example, if you look right up the middle, I think you can see that you get a strong central maximum going straight out, right? Just to the left and just to the right of that is a place where it's sort of gray. That's where the waves are tending to cancel each other out. Now, if you have a better animation of this here, and it shows it a lot more vividly, that there are directions in space along which you get constructive interference, if you have 2 point sources separated by some distance, and there are directions in space where they tend to cancel altogether. So we would say that these are the directions of the maxima, and then the minima are in between those. You can actually do this with a real setup over here. Now let's see, I might have to turn the lights off a bit. Find where my laser is going. Do we see it on the wall up there? Huh. Let's try turning off the room lights. There it is. It's a little high, so I'm going to raise this up and put this here. Okay, so what we have here is a laser, and the laser beam is hitting this pattern that is made in this photographic plate. And what we have are 2 slits, basically. And with the 2 slits, part of the laser beam goes through one of the 2 slits, and part of the laser beam goes through the other one. But far away, on the wall over there about 15 meters away, what we see is a pattern of dots, right? Try to set it and leave it. There we go. I almost had it. There. These are very, very small, a fraction of a millimeter apart. And what you see is a central dot there where it looks like the beam is going straight through. And then you have to either side of it minima, places where there's almost no intensity. And then just beyond that, you also have more maxima. And if you can sort of convince yourself there might be secondary and tertiary maxima that are visible here as well. Interesting that if we change the distance between the slits, we get a different pattern. Now I don't know if that'll show up or not. Much tighter pattern. There's more series of dots. Those are further apart. Now we're going to be in the business of calculating the angles at which this occurs for light, and you'll actually do this in DL yourself. And next week, when we start the lecture, we'll work on doing that calculation. But this is the phenomenon called diffraction, and it's very important. And it really, as we'll see in the next lecture, led to the great revolution in biology of being able to figure out the crystalline structure of molecules, especially DNA, and now thousands or even millions of other biologically related molecules.